Getting into the lecture proper, I just want to say a few words about the quiz and then talk a little bit about where we were last time. You probably don't want to talk about the quiz. It's okay. This time Joe B won out, not completely, but did perhaps a bit better than class average. And historically, that's exactly as it's always been in this quiz. That you, like pretty much every unified class before you, was able to do the routine application of beam theory quite well, but your level of conceptual understanding of the limitations of it, of how to go about analyzing a non-standard structure, one that you hadn't seen before, was considerably more shaky. And that's perhaps not surprising, because we've really only had that quiz was on less than 10 lectures worth of material, and you haven't had enough time for it to sort of embed in your core consciousness. I don't get down on yourselves about it, because feeling this is something you really should know. You should, but it may take a little bit longer, and the quiz is a feedback mechanism to help that. I'll be around in office hours this afternoon, and if you feel strongly about it, do come and make an appointment, come and see me outside office hours. That would be fine. Last time we concluded talking about buckling, and this is also concluding our treatment of structural analysis. So buckling, an example, one of many examples of an elastic instability, where if we axially load, in the simple case we're considering an initially nearly straight column, we see that it loads up elastically and then bang, it goes unstable on us. If this was a structure, it would represent a dramatic loss of load carrying capacity. We can understand this, and last time particularly we looked at the effects of imperfections on that behavior, and there's no such thing as a perfect column, a perfectly straight, perfectly axially loaded column, so this is the general case, where we found that just as we'd found for a perfectly straight column, the governing equation is still that the lateral deflection, W as a function of x, goes as this combination of sine and cosine and linear and constant terms. But now, unlike the case when we had a perfectly straight, perfectly axially loaded column, these constants A, B, C, and D are actually satisfied, take on non-zero values according to whatever the boundary conditions are. And if we plot out the the lateral displacement, say, of the midpoint versus the load that we're applying, as we get increasing imperfections, so as this load E, as this load P is applied, an increasing distance away from the midline, we get further and further away from the ideal bifurcation buckling behavior that we saw in lecture M12. And depending on how far off, how non-straight, how eccentrically loaded our column is, we'll get a larger and larger deflection at a lower and lower load. But the bifurcation behavior still represents an asymptote. For the simply supported case with pin and roller at each end, the critical load asymptotes but never quite reaches pi squared EI over L squared. And so in the absence of any information about the imperfection we might have in the actual structure, this provides at least some estimate of when this elastic instability will occur. I mentioned something else in passing, and I think I managed to confuse you, that I said that in general, for a perfect column, the critical load goes as some factor C times pi squared EI over L squared, the critical load for a perfectly straight, perfectly loaded elastic column. Where this constant C, I tried to appeal to your intuition about what it might look like for a couple of cases. And that was probably the wrong way to go about doing it. To avoid the confusion, or to address the confusion in the muddy cards, if you solve or assume that this was the solution for some arbitrary set of boundary conditions, you would solve it, and this constant C would just come out of that solution naturally, and you wouldn't have to be assuming anything other than that solutions to the governing differential equation are of this form. So C is just a function of the boundary conditions and the geometry of the problem. Perhaps forget, if it didn't make any sense to you, the intuition I was appealing to, because I think from the muddy cards, for many of you, it wasn't good intuition. It wasn't a good assumption on my part. Are there any questions about buckling, effective imperfections on buckling, before we move on to the next topic? Yes?
What is the word after solution?
Oh, sorry, still. Thank you. Yes, the handwriting is not getting any better. Any other questions? Okay. What we're going to do then is move on to the next and final topical area for you in unified materials and structures. And that's to look at, or to tie together what we've done on structural analysis and start, so from what you've done on structural analysis, you, in principle, for the simple structural members, axial bars or rods, beams, shafts carrying torsion, now beam columns buckling, you can say something about the stresses, stress distribution, the maximum value of stress, and for that matter, the deformation of the structure. But you don't actually have anything to equate that to. So how much stress is too much? How much deformation is too much? And what we're going to try and do in the last 6 lectures or so is tie this, or bring in the material element, understand what governs structural integrity of our simple structures we've analyzed from the material point of view, how the material contributes to that. So before going any further, let's just do a PRS concept question and see if we can recall what we actually mean by structural integrity. And yeah, so it's about stiffness, failure, longevity, cost, stiffness, failure, safety, cost, failure, failure, longevity, cost, longevity, stiffness, and safety. Some other answer, do not know, do not understand. So just to get us warmed up on this topic, what we're thinking about. Just in case I'm not strong enough. How are we doing? Anyone need more time? I guess you either know this or don't. 5, 4, 3, 2, 1, cut. What do we think? Yeah, okay, so the majority think it's about stiffness, failure, longevity, and some of you have some residual memory that safety should be in there. It really is just structural integrity. It's not the design objective, which, if you remember, the design objective for structural design has some mention of cost. It doesn't have a mention of safety. It's achieving structural integrity while minimizing cost. Structural integrity is the, if you like, the technical part of this. It's how much deflection are we going to get for the loads we're being asked to carry, asking our structure to carry. So that's about stiffness. We obviously don't want our structure to break into 2 pieces or to collapse on us. It's about resisting failure. And we want it to last a decent economic length of time. We want it to have certain longevity. So the correct answer is number 1. Any questions? Particularly those of you who had safety in there. Safety is an economic consideration, remember. Hard to take, I know, but we've debated at length. Yes, Scott?
Well, I was just going to ask, don't you sometimes design structure to fail at a certain point?
Yes, in a sense. you certainly don't want a structure to carry, to have unnecessary strength, because by and large, additional strength means additional material, additional weight to the structure, and if it's a flight structure, you're going to pay an economic penalty for that additional weight. So you want it to hit its design loads with maybe some small margin of safety, and that's a technical term. The margin is what the designer builds in to exceed the requirement, so that if he's made or she's made some error, that it's accounted for. But no more than maybe 5% on the ultimate load that you're asking your structure to carry. It's an important question. Other questions? Okay, so we've talked about the first of these last term. We've talked about elastic behavior of materials. So you know at least where the Young's modulus or Young's modulus, shear modulus, Poisson's ratio come from, which are going to govern the deflections, extensions of bars and rods, and deflections of beams and angles of twist of shafts. What we're going to talk about now are the materials aspects, the constitutive behaviors that relate to these other two aspects of structural integrity, namely failure and longevity. And just as we had last time, that there are three objectives, and these are the same three objectives as we had at the end of last term when we talked about elasticity. The first one we've already mentioned. It's to allow you to understand what places the limits on the loads, the stresses a structure can carry, how the material, brilliant, how the material plays into that. Then to allow you to understand the origins and limits of the strength of the material. So just as we looked at atomic structure, crystal packing, atomic bonding to look at the origins of Young's modulus, we're now going to do the same thing but where strength comes from. And then finally, to allow you to select materials for a specific application. That we've looked at for a axially loaded rod, we might want for maximum stiffness high Young's modulus over density, but for a beam in bending, we want a high value of Young's modulus, square root of Young's modulus over density, and we're going to explore those same relations for strength and also to prevent fracture occurring. But before we get sorry, one final thing. Just be a little bit careful that, and this sort of ties back to the quiz, that, or part of the quiz, that when we define, we need to distinguish between the material response and the structural response. If we're designing an airplane or a launch vehicle, satellite, whatever, we're really ultimately interested in structural performance, and we're interested not so much in the material failing or the material being stiff enough. We're interested in the structure failing or the structure being stiff enough. Failure of a structure may have nothing to do with the material that it's made of, and a good example of this is buckling, which is a collapse of the structure, but it owes something to the stiffness of the material, but a lot more to the geometry, the length, the cross-sectional dimensions of the structure. So when we talk about failure, it's failure to meet a structural design purpose, not necessarily just a material failure, although that's often part of it. So before we start talking about failure and sort of developing analytical models for it, I wanted to just look at the phenomenology of failure, of metals particularly, which is mainly what we're going to concentrate on here. And just to note that depending on what we do to it, a material may behave in different ways. And you sort of know this already. Here's a paper clip. It behaves elastically. I can use this paper clip over and over again. It just provides a little bit of spring stiffness, holds the papers together. But we've all done it in our idle moments. We pull it apart, and it deforms plastically, which is a permanent deformation, so that I've opened it up, and I can try and get it back, but it's never quite the same again. You bend a piece of metal beyond its elastic limit, it's permanently deformed, it's failed, at least for this purpose, and then I get mad at it, and I do some cyclic loading on it, and at a few cycles, just bending it backwards and forwards, it breaks into two, and that's a fatigue failure, a failure under a repeated cyclic load. So same bit of metal that was performing quite happily, elastically, holding my papers together, overloaded, plastically deformed, and then repeated cycling, it failed. That's the essence of what we're going to be looking at, what governs those different failure processes. A couple of other examples, just tied into the little bit of modeling we're going to do. And this may or may not work, depending on how strong I'm feeling today. Here's a bit of metal. There are not many bits of metal I can do this with, but this happens to be a bit of solder. And what I'm going to do is an impromptu tensile test. Actually, Carl, can you... better still. Hold it low, so it's actually if you... yeah, OK. So we're going to pull, and we're going to try and break it. Is it slipping at your end, Carl?
It's really hurting.
OK. OK, that was worth it. That was worth it. OK. If we put it down, look what's happened. This initially...
This is lead-free solder.
Sorry about that. No, but look what it's done to the notch in my hat. OK, what you can see is, or I hope you can see, just hold it there a second, is that as this has failed, that the solder has thinned all the way down to nearly to a point. It's that process we're going to has a technical name of necking. That's what I didn't want to do. OK, and you'll say, well, this was just a soft solder, so it's not representative. But if we took a piece of steel, and I'll pass this round, you'll see a very similar thing that, OK, you can, thanks, yeah, that hurt me too. Action and reaction comes in there, so at least our pain was equal. You'll see a piece of steel, which was pulled in a tensile testing machine, has also necked down significantly, maybe not to a point, but still a significant reduction in area around the point where it's failed. I'm going to do another tensile test, but this time on a piece of aluminum, or aluminium where I come from. And I think I can manage this one on my own. I'm going to pull this, and you can see, oops, that's actually not necking. That's, oh, right, OK, there it goes. Always fails near the grips. That it bent up on me because I wasn't holding it flat. But you'll see that actually this time it failed in a pretty brittle manner, that there was no appreciable reduction in area, at least in the width of the specimen. It just failed suddenly straight across, as opposed to the solder that necked down and then failed, admittedly quite catastrophically for Carl and me. So this is aluminum. This is the material we build aircraft out of, admittedly very thin, but it's essentially the same material, probably not as strong an alloy as we use to make aircraft out of. So how come this steel is, and the solder is quite ductile, it necks down, it deforms, whereas the aluminum fails by a fracture process? A couple more, just if you didn't see what I did then. This is modeling clay, and I'll try and load it just so you get the idea of what's going on. You see it's thinning down, it's plastically deforming, and oops, it always does that. Yeah. And it necks down nearly to a point as we're drawing out material. This is actually a plastic instability, and we'll talk more about that by the end of the lecture. So there are different material behaviors here. There's this sort of plastic response, and then there's a brittle response. I'm going to do one more example to concentrate the mind. I should have... I've got a slight cold, so this may... If I'm looking red, it's just a reflection of this, OK? But it's got a leak, I'll swear to it. That's enough. This, despite what you may be thinking, is not a balloon. OK, you've got to use your imagination. What do you see here? A pressure vessel. OK, that's good. You could be a mechanical engineer. What do you see here?
Fuel tank.
Fuel tank. Cryogenic Fuel tank, maybe. Yeah, pressurized. We talked about that last time. So that's the sort of space launch vehicle person. What about humans in space? What do you see here? You see a pressure vessel. I see the International Space Station. Okay? And what do I see here? A meteor. Yeah, now you're going with it. So a very thin-walled very thin-walled pressure vessel, and something that's going to approach it at high velocity. And I don't even need to do this, right? Yeah, or I see an aircraft fuselage, which is also pressurized when you're at altitude. And by the way, an aircraft fuselage, and for that matter, the International Space Station, has a thinner wall compared to its diameter than this balloon does, as I've got it pressurized here. Comforting thought next time you go up in an aircraft. You hope they have been properly designed, so this isn't going to happen. But in that case, aircraft fuselage, turbine blade, or in fact a fan blade or compressor blade that gets thrown out from the disk, an uncontained disk burst, and it goes. And you'd really rather that didn't happen if you're an astronaut in the International Space Station, passenger in row 13A, which is the blade-out row in a 737, or if you're sitting on top of a Saturn V launch vehicle. Why did that happen? I just put a little hole in it, and bang, I got a very catastrophic failure. It ties back to what was going on with this piece of aluminum, that it just went bang, it failed straight across. It's a fracture process as opposed to the steel or the modeling clay, which is our prototypical metal or model for a metal, which had this ductile response that they neck down, they undergo permanent deformation before they break into two pieces. So that's what we're going to look at. And it's very important to understand that there may be different failure mechanisms depending on what material we're looking at. And also, we need to know what we can do about preventing those failure modes, or from a material point of view, to what extent can we make materials stronger, more resistant to failure. And we'll move on and talk about fatigue in due course. Any questions? Ash?
More of curiosity. Will the plane actually fall like that, or is it more likely to be the way in the movies that everyone gets sucked out of it?
Time for one of my favorite anecdotes. Aircraft, by and large, are designed not to blow up like that. Aircraft are designed not to blow up like that, okay? And it's what's known as a damage-tolerant design approach. And in particular, it's designed for that specific, or one of the design criteria, is that the fuselage could get punctured with a pretty large puncture, for instance, due to a blade out or a fatigue crack that's grown. We'll talk about fatigue later. So you have ribs that go round circumferentially down the fuselage, and they provide overall stiffness, but they also, very importantly, provide a barrier beyond which a crack shouldn't grow catastrophically. But you can still get cracks, and you still occasionally, very occasionally, get an unconstrained blade out. And there was a case of a DC-9, I believe it was. This isn't my story. I'll give credit to Alan Epstein, who told me about it, which was flying domestically around the States. And it suffered a disc burst in the engine, and DC-9 has the engines at the back, and it shot one of its, I guess, fan blades through the fuselage, and you lose pressure, but it wasn't a catastrophic failure, and got down to low altitude, and did an emergency landing, but it was basically fine. Then this was a while ago, before they were quite so disciplined about counting everyone on the plane, and the flight attendant saying, "Well, wasn't there someone in that row 28? Wasn't there someone in 28H?" And they were scratching their heads and they couldn't quite remember. And it was only when they got to the manifest that there had indeed been someone sitting in that row. And they were close enough to where the blade went through that their mortal remains got sucked out somewhere over the Midwest, which is not a very nice thought. But anyway, thank you for asking that question. Any other questions? Curiosity is good. Yes, Ben.
There's some movie where the airplane rips off.
Ah, no, that's not a movie. We will talk about this particular case, and it's actually a success story. That a Boeing 737 flown by Aloha Airlines, I think it was in 1990, became the world's first convertible commercial jet, as it lost a large part of its upper fuselage forward of the wings. And I'll bring in pictures when we talk about fatigue. It was accumulated fatigue cracks that basically caused perforations around the fuselage, and the upper fuselage got ripped off. But miraculously, even though it had lost nearly half of the circumference of the fuselage in that region, the plane still was able to get down and land safely. There was one casualty of a flight attendant who was standing up and got whisked out at 20,000 feet. But everyone else survived, and it really is a remarkable story of very solid structural design that was able to happen. I mean, I'll show you pictures of this, you'll be amazed, but it's not a movie, that was real. Okay, let's move on and talk a little bit about the first of these failure modes we're going to examine, that of yield and plasticity. And it's the failure mode we saw when we looked at a piece of steel, a piece of plexiglass, a piece of modeling clay, and this piece of solder deforming, necking down, undergoing permanent plastic deformation before failing. So this is lecture M15, and it's yield and plasticity. And I'm going to do a little bit of naming of parts, and I wish that you had an opportunity to actually go down into the lab and do some tensile testing on some pieces of material. We've done this in previous years. Unfortunately, we don't have time in the systems problem schedule to do it this year, but if you ever get a chance, don't take my word for this. Actually do a mechanical test yourself on a piece of material. As always, I'm just presenting a model. You should always question it. So the typical test we'll do is what, in a more instrumented way, what Carl and I did over the overhead projector. We have some material, a rod of material, some cross-sectional area A, some length L, and in fact I'm going to call this A0 and L0 because, well, we'll see why in a minute. And that allows us, just as it always has, to define a stress, some stress which is force over area, and some strain which is delta L over L. And I'm going to give these slightly different names. So some stress that's I'm going to call sigma nominal, which is sigma n, force over area, and some strain, which is the change in length over the original length. And what we're going to typically see for a metal is that there's some region in which it's elastic, with Young's modulus E. Then we hit a region where we get plastic deformation, we get yield, the so-called yield stress, sigma y. And after that point, we'll get a nonlinear increase of stress with strain, but with a slope that's significantly less than the Young's modulus. And then at some point, we'll find that we get a maximum in the stress-strain response. usually called the tensile strength, so sigma subscript Ts. So that's the maximum stress the material can carry, at which point, and we'll talk more about this, we see this necking phenomenon, this reduction in cross-sectional area in a very ductile material down to a near point. And then somewhere after that, we get failure, breaking into two halves. Which, again, we see in all those cases up there. So that's the basic phenomenon. If we just took a piece of aluminum or steel and loaded it up, we'd go through these conditions. There's one other thing you should be aware of, which is if we load this up but don't go to failure, we don't go past the point where we get necking, if we unload it from here, I'll just draw this. Oops. We go up past yield to some strain, some stress, and we unload. We unload with the Young's modulus that we started with, and we get some plastic permanent strain resulting. And then if we reloaded this up, or went back up here, we would reload again with the same modulus of that material. The modulus doesn't change because of this plastic deformation until we hit this yield stress, this new yield stress. The material has apparently got stronger because we've done this deformation to it, and would continue on until we get tensile failure. Yes, Ben? No, it's actually to the nth significant figure true. And it's because, as we'll see, that we aren't fundamentally changing the crystal structure or the atomic bonding, the things that control the Young's modulus. We're just rearranging where those bonds are as we do this, and we'll look at the mechanisms that underlie that. Yes?
What's the subscript for the sigma right below that? Yes.
I will just do a little bit of naming of parts here on the screen. So there's the stress-strain curve that I sketched, and these are in the notes. And we have yield strength sigma y, tensile strength sigma subscript Ts. There's some permanent strain after unloading, so some plastic strain. And unloading and reloading is a linear elastic behavior. And then once we go beyond yield, initially, we get this increasing strength with more deformation. And this is so-called work hardening. So increasing yield stress with increasing plastic strain. Any questions? Everyone buy that? Yes, David.
Well, is it ever the case in manufacturing that someone might purposely stress something past yield and make it strong?
Absolutely. Absolutely. And in fact, there's no metal that you're going to use as an engineer that hasn't been deliberately work hardened in order to get a certain yield stress. What are examples of this? What might you do to work harden a piece of steel, or even this foil has been work hardened? How do you make foil? Anyone?
Just basically roll it into sheets.
You just basically roll it into sheets, but the deformation you're doing is plastic deformation, because you don't want it to spring back elastically. You want to permanently reduce its thickness. So this has seen a lot of plastic deformation. In fact, you more or less reduce it all the way up to this point, which also explains why there isn't much additional deformation. When I pulled on this foil, it broke in a pretty brittle manner without much additional plastic deformation occurring. How else might you do work hardening? Who are the first metal workers? Blacksmiths. When you hit things, what you're doing, what you're whacking the metal is increasing its strength. You're turning it into a shape, sure, but the difference between doing it hot and doing it cold we'll understand in a few lectures' time, but hitting it whilst it's cold will push up the strength. Obviously, there's a trade-off. You don't want to make it so brittle that it shatters if the horse gallops its foot onto a stone. But so that's the blacksmith's art. Tempering. There's some other things going on in metalworking steel. There are phase transformations, which we're not particularly going to talk about here. Yeah, Ben.
I was curious about why the curve dips down after the maximum stress.
We'll come on to that. Basically, it's run out of work hardening capability. You can't make it any stronger. So failure starts to occur. We'll look at that, but hopefully before the end of this lecture. Up to now, we haven't really distinguished between tensile and compressive behavior, but we're going to need to, for reasons I'll hopefully demonstrate here, that if I take now a piece of material that I'm going to load in compression, I can only do this once, so 2 blocks of metal, I'm going to start pushing. What happens? What are you seeing happen? It's expanding, and it's going to continue to expand, and I can go so far, but at some point I just can't continue to compress this. It's barreling out and it's extruding upward as I do this plastic deformation. It's fundamentally a different behavior from what I've got here, where I don't see this necking down in compression. And why not? Why don't I see this necking behavior when I load in compression? What's happening as I deform in compression? That area, what's it doing? The area is increasing, so if I had this behavior, the load I have to carry is continually increasing only because the area is increasing. So it's not that the material is necessarily behaving any different in tension or compression, it's that the way we've defined stress and strain is no longer adequate. Why not? What's the limit on our definitions of stress and strain up to now? What's one of the key limitations where our model for strain and displacement depends on? Jonathan? It's got to be a long beam. No, we were looking. Remember we defined we defined strain displacement relations for this infinitesimal cube of material or square of material. Fluid. Yes, so long as we're dealing with small deformations, sort of less than 10%, ideally less than maybe a couple of percent strain. And what's the strain here? What strain did I put this through? Well, what fraction did the length change by? About a factor of, or it halved, so it went to 50% strain, or if I did it in reverse, it would be 100% strain. So strains are 0.5 or 1 or 2. Those are big strains. So we have to be a little bit careful about how we define our reference for the length. And just plotting delta L over L0, and for that matter, force or stress in terms of force over area is not quite enough. So the way we get around this, or just deal with this, is just to refine our definition of strain. And introduce the idea of a true stress and a true strain. as opposed to what I had here, which are the nominal stress and strain. And it really couldn't be simpler that the true stress is the actual force over the area at that amount of deformation. So, and the true strain is defined as a differential quantity. It's the differential change in length with respect to the current length, which the definitions are just the same as we had before. It's just that the cross-sectional area and the length are continually changing, or potentially continually changing, as we do these large deformation operations on our material. Elastically, most of the materials we're going to be looking at don't go through large deformations, but in plastic deformation they do, and this allows us to account for that. Just to sort of reinforce how this works, that if we're deforming material from an initial length L0 to some current length L, then we're going to need to integrate up all the deformation we're doing. Sorry, excuse me. That this is the increment of true strain is dl over L, so the true strain is therefore the integral from wherever we started, whatever our initial length was, to our current length, and that gives us a logarithmic dependence on the ratio of the current length to the initial length. And sometimes true strain is called logarithmic strain because of that. One further thing we can do to tie these two ideas together is to note that in plastic deformation, unlike elastic deformation, in plastic deformation, volume is conserved. That the change in length and the change in area are related because volume is conserved. So we can, in defining the true strain, the current length, we also know that the current area must be scaling with that. And so if we just manipulate the equations, these fairly simple equations. Oh, who made that nasty mess on the screen? We can get expressions that link the nominal and true values of stress and strain. That the true stress is the nominal stress times 1 plus the nominal strain. The true strain is the natural log of 1 plus the nominal strain, just by substituting in these expressions for true stress, true strain, and the fact that volume is conserved. Any questions? If we do that, if we plot true stress against true strain, we find that materials look more or less isotropic between tension and compression. There are some important exceptions to this. But we won't And what's happening here is that we're just continuing to increase the force, continuing to increase the area, but we're not increasing the stress and we're not increasing the strain. Any questions? Okay. Suppose we did this test. Suppose we applied tension or compression loading to a circular cylinder, circular cross-section cylinder. What would be the work we would have to do in order to deform this cylinder to some stress and strain on our true stress, true strain curve? So the metal cylinder is loaded by uniaxial tension past its yield point, so we're somewhere up beyond this elastic region. How much work did we have to do? And choices, it's the area under this stress-strain curve, the area under the stress-strain curve multiplied by the volume of the cylinder, the stress times the strain times the length of the cylinder, the strain times the stress times the cross-sectional area of the bar, the maximum stress times the area times the strain times the length of the bar, some other answer, and you've lost me. Yes, Louis.
You mean total length and new length? Or like the extension?
No, I mean the... What do we think? So the majority think yes. Okay, the majority think the area under the stress-strain curve multiplied by the volume of the cylinder, which is absolutely right. That if you took this area, which of course is the integral of stress d-strain, that's that's the energy or work done per unit volume. Just by dimensional analysis you can see that, or considering the units of stress and strain. So in order to get the total work done, you'd need to multiply this by the volume of the cylinder, and it doesn't really matter what the length is and what the area is, because we've said that the plastic deformation is occurring at constant volume, so the volume isn't changing as we do this. And this is the explanation of and this is an irreversible process. Thermodynamically, unlike elasticity, which is reversible, plasticity, you're having to do work. It's being dissipated as heat. It's not recoverable. And this is why if you do a rolling operation, if you just do frictional contact between surfaces, which has lots of little asperities on the metal surfaces deforming plastically, the metal's going to heat up by this amount and the thermal conductivity of the material. Any questions? We'll come back to this idea of energy, energy of deformation in due course, and particularly when we look at fracture. I'm just going to skip slightly in the notes, but just to set up where we're going to go next. So the two material properties that I'd like you to take away from this lecture are the yield stress and the tensile strength. generally for aerospace design, we're going to try and design, well, we are going to design so our material remains pretty much everywhere below its yield strength. And we're going to rely on the fact that there's some tensile strength that's a higher quantity that is there to bail us out if we got an unexpected overload. And we'll come on to talk about the concepts of limit and ultimate load on a structure in due course. This is a plot of strength versus density from Ashby's material selection book. And what I want you to get out of this are a couple of things. My laser pointer isn't working, so strength in megapascals, density, strength spanning several orders of magnitude here. Here are metals, composites, polymers, ceramics in a dotted dashed line, because generally yield or failure won't get to these levels, because in tension at least we'll get fracture before, and we'll talk more about that. But a couple of things to notice, that unlike for elastic, the Young's modulus, elastic response materials, an individual material, titanium, steel, aluminum, alloys, span a big range, more than an order of magnitude in each case, in the strength of the material, either the ultimate tensile strength or the yield strength. We have a lot more ability to change the strength of a material by changing its composition and its microstructure in strength than we did in stiffness. And secondly, that just as before, metals tend to group, composites tend to group, polymers tend to group. So by understanding the sort of prototypical behavior of one material, we get an idea of what's going on in the whole class of material. And that's what we're going to move on to next time, of looking at how this works, looking at what the different strengthening mechanisms are that get us from a steel that has a strength of maybe just over 100 megapascals, a mild steel, structural steel, up to a high tensile steel, which might be 2 gigapascals, or perhaps of more importance to us, how we get aluminum from 50 or 60 megapascals up to nearly 700 megapascal strength in the high-strength alloys commonly used in airframes. So that's what we're going to move on to next time, as well as just finishing off a few thoughts on this. As you fill out your muddy cards, are there any questions? Yes, Jacqueline. That's a failure stress. So for a metal, it's usually the ultimate tensile strength, this number. For a ceramic or a brittle material, it's the strength at which fast fracture occurs, and we'll understand a little bit that distinction in about 3 lectures' time. Okay, please give me your muddy cards, and I will see you same time tomorrow.